So this is lecture 4. In lecture 4 we will find the Laplace transform of the basic signal, impulse, step and cosine signal and an exponential signal, but here the t is given in modulus. We will take the first signal, that is impulse signal. We know that impulse signal exists only when t is equal to 0. Okay, and this is signal, and this signal exists only when t is equal to 0 and the area of the signal is equal to 1, and mathematically you can say integral minus infinity to infinity del of t dt, okay, is equal to 1. That's the area of the signal is equal to 1, and del of t equal to 0 when t not equal to 0. So the signal exists only when t is equal to 0. So I can substitute here integral minus infinity to infinity del of t e raised to minus st dt, okay, and the impulse signal exists only when t is equal to 0. So we don't want to integrate it from minus infinity to infinity, okay, or we can apply the property. Based on that property, for example, if there is a signal x of t into del of t minus t0, and it's from minus integral, so minus infinity to infinity dt, so answer is equal to x of t0, okay. So based on this property we can write, so the equation, the answer becomes e raised to minus 0, so e raised to 0 is equal to 1. Or we can say simply we can evaluate this integral, the signal exists only at t is equal to 0, so we can evaluate the signal when t is equal to 0, okay. In this way also we can think, so the answer is equal to 1, so there is no restriction for this. So the ROC is entire is at plane, okay, not S plane, not is at plane, it's S plane, okay. Now we will discuss next question, that's a step signal, okay. Here you can see that step signal is defined as u of t is equal to 1 for t greater than 0 and 0 for t less than 0, and you can draw the waveform, and this is a point 0. From 0 onwards the function magnitude is 1, so this is step signal. So I can substitute here integral minus infinity to infinity u of t e raised to minus st dt, okay. Now we know that the signal exists only from 0 to infinity, so I can simplify the limit from 0 to integration from 0 to infinity, and e raised to minus st dt, okay. So now we need to apply the limit, t tending to infinity, so e raised to minus st dt. So in order to get a converging answer, we will take two cases. The real part of s should be greater than 0, this is one case, okay, and means s is positive. So if s is positive, this quantity is positive and it's infinity, so you can write e raised to minus infinity, which is equal to 0. And the second case, we can consider real part of s less than 0, means is negative, so e raised to minus and negative and infinity, okay, t is equal to infinity, so it becomes e raised to infinity. E raised to infinity is infinity, so we will not consider this case, we will consider the first one, or we will substitute the answer is equal to 0 when you apply the limit t is equal to infinity, okay. So we need to write one more step. After this we can write e raised to minus st, so this is a case, it's 0 to infinity divided by minus s. So we already know that we will take only one case when limit t is tending to infinity, we will take the case 0, okay, the answer is 0, and we prefer this condition, and we can write it becomes 0 minus 1 by minus s, or we can write 1 by s when the real part of s is greater than 0, or we can write sigma greater than 0. Okay, so this is ROC. So when you take the S plane, in the S plane, when you analyze this particular case, you can see that okay, this side is actually positive, sigma is positive in this side and sigma is negative in this side, so this is 0 reference. And here you can say sigma is greater than 0, means towards right. Okay, so this is the ROC, right side of this j omega axis. Okay, this is about E of t. And another way also we can do this particular problem, and we know the result of an exponential. So this is standard waveform. Okay, if you know this result, in this case, now we need to find simply U of t. We need to find the Laplace transform of U of t. We know the result of e raised to minus at into U of t. Here if you substitute this a equal to 0, so you will get simply when a is equal to 0, the result is becomes U of t is 1 by s, so a is equal to 0, and the ROC become real part of s greater than 0, or we can write sigma greater than 0. Okay, in this way also we can approach. And next signal is cos omega t into U of t. Okay, and it's a bilateral transform. So if it is a bilateral transform, definitely there will be a term called U of t into cos, not simply cos. Okay, it's not possible to evaluate if it is a bisided. So always check whether there is a U of t. Now we can substitute here, it's from minus infinity to infinity cos omega t into U of t, that's a signal x of t, and now we need to find the Laplace transform, so just multiply with e raised to minus st dt. So this is the basic equation. Okay, and you know that the signal is U of t if U of t is 1 for t greater than 0 and 0 for t less than 0, so we will get like this. This is a waveform. Okay, so we can simplify this integration. And one more point, this cos omega t can be written as e raised to j omega t plus e raised to minus j omega t by 2. Okay, by Euler's formula we can write. So we can substitute here. So and here this minus infinity, we don't want to integrate from minus infinity, it's only starting from 0 because U of t exists from 0 onwards. So I'll write like this: 0 to infinity, the first term is e raised to j omega t into e raised to minus st, and there is a 1 by 2 and dt plus 1 by 2 integral 0 to infinity e raised to minus j omega t into e raised to minus st dt. Okay, so now we can integrate this. So first we can group this term. So 0 to infinity e raised to minus s minus j omega into t into dt plus 1 by 2 integral 0 to infinity e raised to minus s plus j omega into t dt. Okay, now we can find the transform, but there is a condition. It's 1 by 2 into e raised to minus s minus j omega into t divided by minus s minus j omega, and we need to apply the limit. It's from 0 to infinity plus 1 by 2 e raised to minus s plus j omega into t and minus s plus j omega, and the limit is from 0 to infinity. Now we can see there are two cases, and we will always choose the converging answer when you apply the limit t is tending to 0. So in the first case, in the first part, we can take s minus j omega, or real part of s minus j omega greater than 0, or in simply you can say it's sigma greater than 0. So there can be confusion that omega, if you expand, s is equal to sigma plus j omega, so we can call it as w. Okay, so this is w actually, or you can put omega 0 here also. So this is omega 0 and always omega 0. This is not omega, it's actually omega 0. Okay, omega 0. So here also it's omega 0, and here it is omega. So I'll write it, rewrite this particular side. So real part of sigma plus j omega minus j omega 0 should be greater than 0, and we know that only the real part is sigma, so we can write sigma greater than 0. If sigma greater than 0, you can write the transform of this particular portion like this: 1 by 2 1 by s minus j omega. So after simplification you will get the transform of this particular portion as 1 by s minus j omega and sigma greater than 0. And the second portion, again, if you simplify this, you will get 1 by 2, and we can think about s plus j omega 0. Okay, the real part of s plus j omega is greater than 0. That is, again you will get sigma greater than 0, and the transform will be 1 by s plus j omega 0. Okay, so we got two terms. In both cases sigma should be greater than 0, and now we can conclude. The final answer will be like this: x of s is equal to 1 by 2 1 by s minus j omega plus 1 by s plus j omega, and there is a condition for ROC that sigma greater than 0. Okay, and if you simplify this, you will get 2s divided by s square plus omega square. Okay, so the final result will be like this: s by s square is not omega, is omega 0. Okay, here also it's omega 0. Okay. And the ROC sigma greater than 0 means, if you take the s plane, this is sigma is equal to 0 and ROC is sigma greater than 0, means right of the j omega axis. So this is the ROC in the spine. Okay, it's a standard result. We need to remember this result to find the inverse Laplace transform, and sometimes we need to apply this result also. Now we'll discuss another question, which is e raised to minus modulus of t. First we will see what is the signal e raised to minus e modulus of t. Okay, there's one more point here. This a is positive. Okay, and later we will discuss what happens if a is negative. And if we take a graph with time in x-axis, and when there is a quantity modulus, means here it is positive, here it is negative, t is positive and t is negative. We need to consider two equations in positive side and negative side. Okay, now it is t is positive here, so we need to write like this. Here we need to consider t as positive, so t is positive, so you will get the signal e raised to minus at. Now we will take this negative side. In negative side, this t will consider as minus t. Okay, that's the meaning. So it becomes e raised to at. Now we'll see what's a waveform look like. And at t is equal to 0, it's e raised to 0 means it's 1. And when t is tending to infinity, the equation becomes e raised to minus infinity, which is equal to 0. Means it's a decaying exponential signal. And on the left side, if here t is tending to minus infinity, because it's the negative side, so if you apply the limit, it becomes e raised to minus infinity, which is equal to 0. Means in the left side also the signal is converging, again a converging exponential signal. Now we can apply this signal. So integral minus infinity to infinity e raised to minus a modulus of t into e raised to minus st dt. Okay, now the signal is can split the integration. If you split the integration, it becomes minus infinity to 0. The signal is e raised to at into e raised to minus st dt, and from 0 to infinity the signal is e raised to minus at into e raised to minus st dt. Now we will get two signal. We can consider the two signals separately, and first we will take the first part. So we can take the first part, integral minus infinity to 0 e raised to minus s minus a into t dt. Okay, if you do this integration, it becomes e raised to minus s minus a into t divided by minus s minus a, and the limit is from minus infinity to 0. So definitely there will be two cases when you apply the minus infinity limit based on this s minus a. So I can write here, limit t is tending to minus infinity e raised to minus s minus a into t. Okay, and well, first we will consider the case the real part of s minus a, that is or simply we can say that s minus a is positive and negative. So if s minus a is greater than 0, okay, that is positive, so e raised to minus here it is positive and t is negative, so as a total you will get e raised to infinity. E raised to infinity is equal to infinity. So we don't prefer this particular case, and next we will try real part of s minus a is less than 0. If that is less than 0 means e raised to minus, then next quantity is also negative and minus infinity if t is minus infinity. So you will get e raised to minus infinity, which is equal to 0. Okay, and here if real part of s minus a less than 0 means you can write sigma plus j omega minus a less than 0, or real part of this, or you can write sigma less than a. Okay, finally you can get sigma less than a. This is one condition, and if in that particular case you can apply the limit. So first e raised to 0 minus, now if you apply t is equal to minus infinity limit, so we prefer the second case. Okay, this one, so the answer will be 0. Okay, so we can apply 0 result and minus s minus a. Okay, and the condition is sigma less than a. Now we will consider the second integration. In the second integration, it's from 0 to infinity e raised to minus, okay, here also after simplification you will get 1 by s minus a, as a minus also. Okay, and if you simplify this integration, it becomes e raised to minus s plus a into t dt. Okay. And if you integrate this, e raised to minus s plus a into t divided by minus s plus a, and the limit is from 0 to infinity. And again there will be two cases, limit t tending to infinity, this e raised to minus s plus a into t can take two values based on this real part of s plus a greater than 0 and real part of s plus a less than 0. So if it is positive, that is greater than 0, positive, and if you apply the limit infinity, it becomes e raised to minus infinity, which is equal to 0. So we will prefer this particular equation. So sigma plus j omega plus a greater than 0, or sigma greater than minus a, because we are considering only the real parts. And the other case, definitely it will be infinity, because the real part of s plus a less than 0 means it becomes e raised to minus, negative, and finally infinity. So it's finally infinity. So you will get this answer like this: 1 by after simplification you will get 1 by s plus a, and sigma greater than minus a. So you will get two equations. Okay, one answer is like this: 1 by minus s minus a, another one is 1 by s plus a for sigma greater than minus a. So now we'll conclude based on this ROC. So one at minus a and another one at a. So one signal, that is from the previous page you can see that one signal is 1 by minus s minus a. Okay, and the second one is 1 by s plus a. Okay, so we can simplify this too, and the first signal converging when sigma less than a, and the second signal converge when sigma greater than. So we can write 1 by minus s minus a when sigma greater than a, and another part 1 by s minus a, s plus a when sigma greater than minus a. So one signal sigma greater than me means towards right, and another signal towards left. So there is a common area, so you can combine the result, and the ROC, common ROC is from minus a to a. Okay, this is the waveform. So this is the ROC, and you can conclude the answer like this: 1 by s plus a minus 1 by s minus a. Okay. So if you simplify this, you'll get s minus a minus s plus a divided by s square s square minus a square. So numerator, these two quantity get cancelled. Here again I made a mistake. It's not plus a, it's actually minus a. So it becomes minus 2a divided by s square minus a square. Okay, and the ROC is minus a to a. And finally I will give you some practice question. One signal is sinusoidal signal, just like cos you can approach. This is minus u of minus t. Okay, it's a time reversal signal and there is a minus also, and this is simply u of minus t. Now the last question, e raised to minus a modulus of t, but here a is negative. For example, if you want to plot this signal, you can use this minus 2 or something, or you can do in general form also. The solution we will discuss in the next lecture.